circle diagram, the one that makes it go counterclockwise goes on the bottom?
The clockwise one is on top.
Oh, okay.
The anti-clockwise one is at the bottom.
Okay, and
right? The clockwise is on top, and the anti. So point X where we are talking now, you say it's going anti-clockwise, right?
yeah.
Right. So that's why X is over here, where I just highlighted.
Okay, thanks.
Right. So the Y is going to rotate in a clockwise, right? That's why it's at the top. Okay.
All right.
Okay.
Thanks.
If not, watch the video again. You can catch hold of it. Okay. But it's okay. You ask now. It's fine. Okay. Now, let's look at an example. Anyone, any question before I go on? Are we okay? That is why the normal stress is straightforward. Everyone get it. The shearing stress, not a lot of people understand, but now I believe most of you will understand now. And as I say, it's only important when it is carbon fiber. Okay, because carbon fiber, different strength in different direction. Okay, in ordinary metal, aluminum, steel, blah blah whatever, okay, those that are in a solid material does not matter at all. Okay, so I by the way, I made a correction. Okay, polymer somehow is directional also. Okay, it's not just it is. Okay, right, let's look at example number 1. Okay, example. So what I want to do for example number 1, okay, I want you to be able to relate the stresses, okay, from element to Mohr circle. Okay, so this you can do already. Of you can do it. Okay, you can relate element to Mohr circle. And I'm going to go further. And from Mohr circle to element. Okay, I want you to be able to do both ways. Okay, I want you to be able. Okay, so now let's do look at our first example. Okay, let's go into our first example. So again, we have our transformation. So this is our X, and then we have our Y. Then I'm going to draw an element. Okay, so that is our element. I'm going to zoom in so you can see better. Okay, so this is big enough. So that is our element. So our element has this corresponding stresses. So it's going in this direction by 60 megapascal. So this is what we measure in our strain gauges. Okay, we put strain gauges in our component and we measure all this. And our structure is loaded in 2 directions or 3 components. 90 megapascal. Then we have a shear, okay, of 30 megapascal. Right. So what we see from here is we know that stress X is equal to minus 60 megapascal. Stress Y, we have positive 90 megapascal. And like what I mentioned to all of you before, that shear XY is equal to shear YX, and this is equal to positive 30 megapascal. Right, the 30 megapascal is positive because if you look at the previous page notes, is under positive shear configuration. That's why it's positive 30 megapascal. But in terms of shear, it does not matter whether is it positive or negative. It all dependent on the rotation of the element, right? Okay, so we're going to label this again. This is your point X. Standard protocol, nothing changed. This is point Y. Okay, then from here, the question 1 asks, we're going to find Okay, we're going to find principal stresses. We want to identify the principal plane. We are going to identify the maximum in plane shear stress. Right. Then we are going to find the orientation of the element. We're going to sketch the orientation of the element. Okay. Where shearing stress or where shear stress is equal to 0. Okay. So now we have magnitudes now. Okay. So what does all this value actually means? Okay. So with that, we are going to construct our mole circle. Okay. So we are going to construct. I'm going to move to here so you can see how we actually draw the mole circle. Okay. So again, we have our axis. I'm going to draw my y-axis first. So the y-axis is shear, element rotating in a clockwise direction. So 100, 80, 60, 40, 20, 0, 20, 40, 60, 80, and 100. Okay, I don't think you all can see 100, so I'm going to scale this down so you can see everything when I draw it. Okay, you can see everything now. Okay, so that is our vertical scale. Then on a horizontal scale, you have to ensure that the interval are the same. Okay, so these are x-axis. So this is our normal stress, 20, 40, 60, 80, 100. Okay, maybe yeah. So then we have minus 20. Okay, I miss out my minus sign. Okay, minus 40, minus 60, minus 80. Okay. So this is our, so you have to ensure that the intervals are the same. If you don't use the interval, you will not get mole circle. What will you get? Any idea? Anyone? If you don't, if the skip, yeah, you get more over. Okay, there's no mole circle anymore. We clear? Okay, you will get more over. Okay. So we know that so we are going to draw our stresses now, right? So stress X is minus 60. So we're going to draw our minus 60 line. Okay. So this is your stress X line. And then your stress Y line is 90, positive 90. Right. So this is your stress Y line. And then you got your shear. Your shear is 30. And I understand it's positive shear, but we are going to do both ways, right? We're going to draw positive and negative, because whether is it positive shear and negative shear got nothing to do with the position of the shear. Is more on the rotation of the element. Okay. So over here, I forgot my rotation of my element is going anti-clockwise. Right. Okay, so before we construct the circle, the first thing we do, we can we can immediately calculate the center of the circle, right? We can easily calculate that. So center of circle, right, which is our stress average. So it's an average, right? You take the normal stress of both directions, stress X, plus by stress Y, divided by 2. So what you have is stress X is equal to minus 60. Remember, I told you all these are vectors, okay? Plus by positive 90, and then divided by 2. So this will become 15 megapascal. So 15 megapascal is the center of your circle, okay? So now we know that. Now, so I'm going to use green for my center of the circle. Okay, so we know that it is at positive 15. I know I'm drawing at positive 10 down here. Okay, so this is my, hey, move. Okay. So there's my positive 15. Okay, so now I want you all to focus. I'm going to somehow zoom out that you can see better again. I'm going to do 275. Wonder, can you see the element? Okay, this is good enough. You can see the element. So by looking at, let's look at point X, okay? We know that point X is on the stress X line where it is minus 60, right? Because this is minus 60 in compression. And if you look at this arrow over here, the shear, and if you were to put your finger on the center of the element, can anyone tell me, is the element going to rotate in a clockwise or anti-clockwise direction?
Anti-clockwise.
Yeah, anti-clockwise. So anti-clockwise direction correspond to this anti-clockwise down here. So over here, this is your point X. Okay. And then by observation, you will know that this is point Y. Right. Why this is point Y? Because point X to point Y, the angle is 180 degrees. But let's look at it again. Okay. So now if we were to focus on point Y now, okay, and point Y is sitting on the 90 degrees line. So this is your stress Y, 90 degrees line. And this arrow that I'm highlighting in blue now is going to generate a rotation that is going to be what? That is going to be in the clockwise direction. So that's where point Y is. Okay. So now when you draw a straight line, it will definitely intercept the 15. Okay. And where the 15 it intercept, this is your center of your circle, we call O. Okay. So the next thing we're going to calculate now. Okay, so those of you who have a compass, you can start drawing your circle, right? You can start drawing your circle now. Okay, I don't have a compass. Okay, I still have to calculate. So in reality, if you were to construct this, you can get your shear stress very close, but you still need to calculate. Okay, so I'm going to show you the calculation and nothing to memorize. Okay, so now the next thing we're going to do is we're going to determine the radius of the circle. And the radius of the circle correspond to tau max. Okay, tau max. There's nothing to memorize over here. It's high school math. Okay, that's one thing I like. It's just high school math. Okay, so we know the distance from here to here, right? That distance over there, we know is equal to 30, right? And then the distance from the center of the circle up to here, so you can physically calculate. So is 10 10, 20, 30, 10, 20, 30, 40, 50, 60, 70, and half of it is 75. So what we want to identify now is this distance. Okay, we want to identify this distance. So that distance over there